Recorded.
Yeah, it's like also literless rooms for each server racks.
So welcome everyone to the last session on separation logic. Today, I believe we're going to see all sorts of nasty stuff like effects and concurrency and so on.
Thank you. All right, so we had some representation predicates for lists. Of course, you are in a very expressive logic, so you can make it higher order and combine representation predicates together. So if you have M list of L, you can do in fact M list of R, and so R could be like M list itself if you have a mutable list of mutable lists. And then of course you can recover the normal M list by having some special identity R, and then some other things. So yeah, so I'll go quickly. So if you have a mutable list of mutable lists, you can define this M list of M list thing so you can do two things. You can do like the brute force thing of saying you have an iterated star for every of the values that are stored in the first list. So there would be pointers, and then you do for every of those, K of I points to M list of L of I, and L is a list of lists. But of course, there's a slightly more easier way to reason about this, depending on your cases, of course, but usually it's the case. M list of M list of L would match on L, and when you have cons of X, which is itself a list, and L prime, then the pointer points to X on P prime, X being a pointer to the list X, big X, and P prime is the pointer to the rest of the list of lists. So you can generalize with not list of lists only, but list of anything. So any R, where R is a representation predicate. And so then you have X points to R of X. So this quickly arrow is nothing. It's just to say it's pointing to, but in fact, it's just a syntactic sugar for R, X, small x. So it's just function application. Yeah, so I guess nothing surprising. You can recover it by giving an ID representation predicate. Can you guess what ID could be, knowing that? So this is the higher order one. This is the normal one. So you have to choose R. You have to choose ID. So you have to choose R in this formulation, such that the two definitions are equivalent. Can you guess what ID could be, what R could be? It is simple. You just have to find the right, words. Nope, not GC. So you have to
propositional equality.
Ah,
Propositional equality.
yes, very good. So you want to, you have to relate this X here. Oh, yeah, this X here to this X here, and they need to be related. So this X is your small x here, and you need to say that they are equal. So indeed, you need propositional equality. Okay, thank you. When you do higher the representation predicate, that's one of the cases where it would be good to have the separating implication. So I could have introduced it at the beginning, but it's actually not necessary for most of what I presented. So it's only now on the last day. So separating implication is the magic one.
Sorry, question.
Yes.
If you go back 2 slides, yeah, in the definition of ID, where does the scope of X begin and end? I'm kind of confused.
So this is a syntactic sugar for saying ID is equal to lambda big X small x dot X equal X.
But when you write in the line above M list of IDL, there are no X's occurring in here.
Yeah, ID is a function. You pass it here, it becomes this R,
I see.
and the R is here, so it X points to ID of X, which
I
means
see.
X is equal to X.
But but I see where the small x comes from now. Where does the big X come from? Because the big X is only.
It's the one, it's in
only
your list of
bound-
lists.
So it's a 2-argument function?
No, X is, so if it's, no, it's, sorry, not a list of lists, it's a list of things. In this case, a list of values. So your big X is supposed to be a higher thing, but in fact, it's just a value. So how do you represent it by some other value X? You're saying it is the same.
Okay.
But I think if the function is R, the two-argument function.
R is a 2-argument function,
Yes,
yes.
so X swivel arrow R big X is secretly syntactic trigger for big R applied to little x of big X.
To big X and little x. Because you need to, I mean, if you add more arguments, so it's simpler to make it like a function application swapped. Just, it's easier to read when it's pointing than to put it just at the end. So we typically do that. It is, but it is confusing, so there's a trade-off here. All right, so magic wand. So recall the separating conjunction. P1 star P2 satisfy H if you can split H into two things that are disjoint and satisfy each of the P's. So if you have instead P implies in a separated way Q, it is harder to read. So hold on. So it holds for H if for every H1 that is disjoint from H, P of H1 implies Q of H disjoint union of H1. So the intuition is when you combine P implies Q and P, it gives you back Q. You have some, so that's simple. That's why it's called separating implication, because it's the corresponding for the separating conjunction. Rules are also simple. The interjection rule is you can prove P implies Q if you can have P in your context, but of course it's separated with a separating conjunction. The rule for elimination looks like the rule for elimination of the lollipop in the linear logic, because you need to split the context into two, because you're not supposed to use things twice in separation logic. So this is simple. However, when we try to see it in practice, it can become a bit, I mean, you need to practice a little bit. It can be a bit weird. So I'm giving a few examples, maybe it will be better. So what are some heaps that satisfy the following predicate? So the first one, so there is a pure fact implies 1 points to 2. So I guess I will do something like this. Yes. So you have the definition on top. Yeah. Okay.
1 point to 2.
Yes, that's a good heap. No, so I need to do this. All right. That doesn't work. Yep. This. No. Okay. Separation implication. All right. This here. And I will do that. Okay, very good. 1, 2. The simple heap. 1, 2. So again, I'm mixing up ints and locations. They are basically the same. If you want to do some things properly, you have to distinguish. But remember that on a machine, those two things are the same. So it could be, it makes sense either way. What about 2? False implies separatedly 1 points to 2. All heaps satisfy this. What about 3?
No heaps.
Don't think that's no heaps.
The empty.
Empty heap should be fine. Only heap, only the empty heap. Very good. What about 4? So we're starting to see bits of heaps. No heaps for 4? Maybe some heaps for 4.
What's the precedence?
So it's the same as the normal logic. Conjunction take precedence over implication.
The 2 to 3 heap.
So that's one of the heaps that is good, yes, but it's not the only one. So remember the definition. For every heap that is disjoint with H, P of H1 implies this. So if you have a nasty H, maybe you have something else. Oh yeah, can you see?
Or if H already mentions one
Yep,
as a location.
very good. So indeed 2, 3, this singleton heap, but every H that has 1 in its domain will satisfy this implication. So it's a bit strange, but it's to make it so a bunch of times you will end up in a program where your post condition is implying false because you are in the wrong branch of an F. So you'll have things like this. You have to be able to exploit it. What about 5? Not all heaps. Oh wait, maybe whole. No, maybe.
All heaps of whole 1.
Yeah. Plus the empty heap.
Yes.
What about 6?
All heaps don't mention 1.
All heaps down? That
All heaps where 1 isn't in the domain.
isn't.
1 is in the domain. Is. Oh, yeah.
You need to falsify the premise, so it needs to be there. So all heaps that do have 1 in the domain. What about 7?
Well, 1 have 1.
Yeah, same. What about 8?
That's got to be false, where they're not disjoint, so it's the same, like one with the domain.
Nope, still the same. So you could, if you have false, you can have anything. It's just to mean that this basically excludes anything that has 1 in the domain. Was the lesson. All right. This maybe that's good to have it here. Okay. All right, a bunch of more questions. So you remember heap implication? Those are a bit harder. So you have okay. P implies Q separately implies P star Q. So those two things are not the same. This entailment is a proposition. So you have P implies Q if for every memory, every heaplet, P of M implies Q of M. So that's very different from this, which is a heap predicate. It characterizes some heaps. Like it is not pure at all. This is not a proposition. This is a predicate. So you have resources in separating implications.
Yes.
It holds. Very nice. So how do you prove this?
You know that it's just day convolution of day exponential. Just be like this.
Okay. What about 2? I think you might have seen.
Everybody knows, but not everyone knows why.
Oh no. Okay.
So
So it is not true in weird examples. So if you have P and Q that are false, this is false on the left side. I mean this sorry, this holds for any heap because this is false. But it shouldn't imply P. So if you if you think of it in a logic sense, that makes sense. Just have to forget. So it's both talking about the heaps, but also containing some propositions, some facts, some logic. So you have to not forget that. What about 3? So the parentheses are, and this is the lowest precedence. Also, it wouldn't make sense in otherwise. So the parentheses are here and here. So we've seen some heaps that satisfy the left-hand side before. So for example, this one has 1 in the domain, that's not the left-hand side, so it doesn't imply false. All right, maybe 4. It's a bit harder to read. But maybe not. 1. Who thinks it holds? Who think it doesn't? Okay. So indeed, same thing. 1 satisfied this. H with domain 1. What about 5?
Yeah.
Yes. Why? Okay. Yeah. So yeah, P and nothing implies P are the equivalent indeed. What about 7? Also yes. What about 8? Yeah. So this is a pure fact, so you can put it in those little corners. Yes. What about 9? Also yes. Who agrees with this? Also yes. Yeah. Who disagrees? Indeed, no. This doesn't mean that you have nothing. You could have a heap there. It's the main difference between entailment and separating implication is that separating implication does have some resource inside it. All right. So I guess I can close this. All right. So now that we have this new tool, we can go to the next problem. So in many cases, you have a data structure that have some data structures inside it, and you need to. I mean, splitting is fine, but you have something that is just reading and not removing from what you have. That is called the access problem. So what do I mean? So if you have cons, that's fine. You have a piece on the left, another piece on the right. You cons them. You have a big piece, a big smashed together things. If you have so that's for first order lists. If you have a higher order list, that's the same. You have this little piece of heap. There's just one cell. You have the list, and you have the list of lists here. And when you cons everything, you have just the whole thing. There's no problem. When you do uncons, when you get the 2 parts, like the head and the tail, that's also no problem. You can split. However, if you have this head function, and you know that P points to some non-empty list of lists or list of things, then this specification doesn't hold, because it is not separate. Indeed, you have like a blob inside of another blob. So what do? You can do a weird thing like split this M list of R as a big separated conjunction of everything, but that's awkward to use usually. You can do something that is called like focus before read. So you split this M list of X cons L into 2 things. And then, I mean, you unfold the definition. And so then you can access P.hd, and then you can access this X and use the frame rule to get back all of those things. So that's fine, that works. You have another way that is using the magic one that says, when you do head of P, you get some X that points to this big X, that is the head of the higher order list. And separatedly, if you give me back this X pointing to big X, I can give you back the whole list. So that's fine. Can you see a problem with this? Maybe if R is the representation predicate for references, so what can you do with the reference? What cannot you do with not something that is not a reference, but just a pure thing? So dereferencing is fine. Huh? Freeing would be problematic, yes. Yeah.
So that any kind of mutation might break the separation?
So the mutation would not break the separation, but the mutation is a problem. So if you do mutate this X, so X point to R of big Y, that's fine. It's still separated. However, wait, where am I? However, you cannot just put it back here and get back your thing. So you need to have a slightly different specification that takes this into account. And so you would have something like this, X point to X. And if you give me back X point to any other X prime, then you get this list X prime. So that's one example of the magic wand. We'll see bigger things after that. Okay, that's one small thing. If you have a higher order list predicates and you specify this copy function, you'll have a problem. Why? I should say this is like a copy written like a list.copy, like making a new list, but not knowing what's inside the list. So just a polymorphic copy. Exactly. So it's not a deep copy because it's a polymorphic copy. And so for to make to have this specification, this conclusion where it's separated, you would need to have a function that does a copy of each element for you. And so if you have a copy fp where f copies those r's, and like if basically if it's saying that if f is a copy function for r, then copy f is a copy function for m list of r. All right. Yes, so we should move on. And so of course, if you have a representation predicate, you can combine them. So this is an example where it's a tree with n-ary children that are stored in a mutable list. And so you can do that. I didn't give you all of those definitions, n-ary tree of, n-node of, well, just n-node of. But that's, you can imagine how it works. So when you do iteration, and then you need to specify things a little bit differently. So that's first order iteration, where you have I of nil, you go to I of L. If you have a mutable list instead of a pure list, then you keep the structure of the list unchanged. However, if you have P points to M list of R of L, where L is a list of things and not a list of simple basic values, then it's not enough to have I of nil, because all of those values are things that the function f might change, for example. So you cannot just say, you cannot restrict the specification to f that are unchanging the sub values. So you'll need some other a bit more verbose way of specifying your function. So f of x would take some big X and it can change it, so big X prime. And so how do you specify what X prime is? You keep it in one invariant, and the invariant is keeping track of everything that have been seen and everything that have been produced. Even if this function is not changing the list itself, the function f might be changing every step. So you can do that as well. It's just you have to make your invariance a bit more general. So exercise, maybe that's okay. So that's one instantiation. Inc all, if you have inc, you do inc all by saying iter inc. Blah blah blah. Okay. So I went a bit quickly because this is maybe more interesting. So separation logic is very linear in some way. It doesn't duplicate your predicates. So of course it fits very well if you want to do some resource analysis inside of your logic. So what are some examples of resources? So when you do the allocation, that's one of the memory itself is a resource. So you could control it more precisely. So if you remove from your whole triple the GC part that I've shown you before, so you just remove this part, then you don't have the GC rule, of course. You replace it with a free because you don't have a GC, and free would be R points to some tuple V. You do free of R and you get nothing back. So that's very simple. And then you have a theorem that is also not very hard that says that for every program execution starting in the empty heap, if all of the data that is still allocated in your program, in your actual memory, would be described in the post conditions because you cannot remove things. That also means that proving things in this logic is a bit more of a pain because you cannot throw things away, but you can do it. And so, yeah, corollary, if you have like a pure description of a function, you know that it will have no memory leaks, which is maybe good depending on what you want to do. Yeah.
Can you explain what that lambda with an underscore is?
Oh yeah, lambda with an underscore is we don't care about the result, or more precisely, you could say that the result must be unit. Usually underscore is just we don't care, but it could be. I mean, it's we don't care. It's like a fun underscore or something. Yes.
So I see free as a sort of elimination rule. Can you remind us what's the introduction rule for?
Oh, it would be malloc or ref.
Right. So you need a bespoke introduction for new references.
Yeah. So that's
okay.
So you have references, but it's not enough. It should the real rule is for alloc of an integer. Yeah, maybe I should have that said then. Yeah. Some terminology, so separation logic that have the GC rule are sometimes called affine, which makes sense because it can just throw things away. They're also called sometimes intuitionistic, but I think it's a weird name. There are some justification, but I don't think they're really, I mean, they don't make that much sense to me. Oh yeah, so a simple resource is a file handler. File handler, you're not supposed to throw them away, you're supposed to close them. So if you have a logic that doesn't allow you to, that doesn't have the GC rule, the GC rule, you could ensure that all of the files that you open are closed at the end of your program by a bunch of rules. So you have fopen of S, and it returns you a file handler, such that there exists a list of characters, and F points to a file of L. When you read, it's like popping on this list that you already opened, and you have a close function that just returns the empty heap, given a file descriptor. Okay, maybe more interesting. You can so all of this you need to adapt your interpretation of predicates. You adapt your semantic. You adapt all of your logic to be able to talk about those. It just fits nicely. Like the separation, so you are instead of predicates on memory, it could be predicate on memory and like a list of handlers. It could be predicate of memory plus some fuel of execution. And so that what this does, you can assume that you have a time credits like $X, where X is a real number because you want to be able to do more things, but you could say it's just a natural number, and it represents some time that is that is given to you to do some steps, and then you have every function call, say, or every step that consumes $1. It's kind of nice because you can split X plus Y time credits into X and Y time credits, and 0 is a pure fact. So that works well. So how does that work? When you have you have them in precondition. So if you do some function calls, say array.length, it consumes a constant amount of dollars of time credits. If you want to say that array.make is a linear function, you would say that it consumes an affine number of credits. You can do some more complicated things in precondition, of course. You can do some amortized analysis. Like if you have a stack that is made with a buffer that doubles every time, you need to store all of those credits in your invariant so that when you are actually needed to do the doubling, you'll have enough time credits in your invariant. So the invariant would look something like this. S points to stack of L if this is the description of those two first things are the description of the memory, and the rest is pure facts to be able that you have a bunch of room. You have some room between L and M, and the more you fill up your buffer with things, you accumulate some time credits into this resource. Yes.
Thanks. So is this trick with the credits specific to separation logic?
It is just easier to write it in separation logic because you can, when you call something, when you call a lemma that has some hypothesis about the complexity, you can pass it as a normal predicate, this. And so the frame rule just gives you, okay, yeah, you can pass it. So it's simpler maybe than in other settings, though, to be honest, I don't know many other settings apart from pure just reasoning.
Okay, thanks.
What is more specific to separation logic maybe is space complexity. It is in fact quite trivial to do because basically you're already doing this work when you do separation logic. So it's very easy. You have like diamond size of B, you do alloc B, you get back X points to some, I should have written this is a number, so I should have written like a unit to the B. And when you have the same and you do 3, you get back your diamonds. The same mechanism apply. You can split a plus into a star, a separating conjunction. So what is more interesting is if you add garbage collection, because then you need to be able to reason about everything that points to things that you have not yet freed yourself. So you need to be able to say, I can prove that no one is pointing to this tuple, so that I can know that the GC will be able to eventually collect it, and I will get back some space credits. So if you can do that, it's a bit of, it's hard because you have to keep track of all the routes. So there is a first version with me and Francois, where you have to keep track of every route. You will call them registers. So you have a kind of a functional language, but it's very low level, so it's very strange. And so Alexandre, Arthur, and Francois made something a bit higher level. That's just the same name was high level before. Yeah, what is very useful also is fractional permissions. So you, instead of having R points to V, you have R points to V with some fraction, alpha. You can split the fraction. So if you have, by default, you have 1, but you can split into 2 halves. In general, if you have alpha plus beta, of course, you can split them as well. What is useful, of course, is when you have 2 fractions at the same location, you know that those value must be the same. So this is the agree rule. And of course, the basic operations can be specified in terms of this. And the whole point is that when you read, you don't need the full fraction. You only need a part. You could say, oh, I have not 1, I have just a fraction, but I don't know what it is. But you kind of need to do this accounting of all of the permissions that you have distributed to function calls or whatever, in order to be able to say, oh yeah, I have them have the full permission back, I can say modify it.
So what is one use case? Is a use case, for example, can I read a file and I cannot write to a file? Like what would be kind of a use case for fractional permissions?
One use case could be to say, I want to prove that this function actually does not modify. That's that you pass it a fractional, that's a fraction. If you do concurrency, that's almost necessary also. And that's coming up.
Oh, yeah, okay. Okay, I see the concurrency. Okay, cool. Thank you.
Yeah, so you can. Yeah, so that's one way. If you have concat of A1 and A2, that's also one useful use case. You can, this returns a new array with permission 1 because you just allocated it. But if you had that and didn't have fractions, you couldn't use it with the same array. You need to have a different specification with the same array. But it's kind of a pain. So there are some way of doing, like, to have a modality that is called read-only for your information, but I won't describe it. What is more interesting probably is some parallelism and concurrency. So it seems like separation logic was almost invented for this, but it was not. So, okay, so say you have a parallel pair. So you could have a T1 parallel T2, but we're returning values. So we have a parallel pair instead. So we don't have two threads in parallel, but you have two threads to spawn and you wait for the results. And so T1, T2 return a pair. Just yeah. So you could, for example, optimize the sum between I of an array between I and J by calling recursively the sum function on two different parts of one array. Of course, if you do that, you're spawning many threads for just summing one or two elements, so that's not very nice. So you can just have a cutoff. And of course, you don't have to do sums, but it's in general you have a map reduce with a condition of plus associativity. Thank you. And so what's the reasoning rule for parallel pairs? It is very nice. You have H1 T1 Q1, H2 T2 Q2, and for the pair T1 T2, you have H1 star H2 and Q1 star Q2. The star being, how do we talk about the return values? The return values is actually a pair. The first element satisfying the first Q, the second element satisfying the Q2. So that's very nice. So it restricts when you spawn threads to act on disjoint parts of memory. So that seems like a very strong restriction, but you kind of need a bit of that at least. So with fractional permission, it helps a lot. If you don't have separation logic, you might be able to have some rule like this, but you would need some non-interference conditions, like this predicate doesn't talk about anything that is modified by this other thread, and so it's complicated. So in separation logic, there is no sign condition, it's just this. So of course, if you do that, it's complete. So the memories are disjoint. So the threads, when you write a parallel program, typically, I mean, it could be just parallelism. There is no sharing between the threads, but you could want to have some sharing of some parts of memory. So you can do that with fractional permission, but you could also want something more, which is transfer some parts of memory from one thread to another. So you do this with some kind of synchronization. And so one example of synchronization is locks, like a mutex locks. So say you have this program, R is equal to ref 0, S is equal to ref of N, and you create a lock. You have this function, concurrent step, that acquires the lock, increment R, decrement S, release the lock. If you need to have some, you need to reason about those, because when you, to be able to transfer memory from one thread to another, you do it through locks. And so the resources need to be related to the locks, basically. So you introduce a new heap predicate, P points to lock of H, that says that P protects this resource H. And it's a resource saying it could be this footprint in memory, but we're in a separation logic, so we can say more than this. So we could say that P protects R and S, but also the value that are stored in R and S are related by this logical thing. So R points to I, S points to N minus I. And so every time you call this function, you would reach there, reason about I and increment and decrement, change the I and maintain the lock. I have actually rules. Yes, okay. So those are the rules for locks. So you have this P points to lock of H. It is important that this predicate is duplicable because you need to, access it from different parts of the memory, from the different parts of the program. And so what are operations for this? So if you have H, you can create a lock and just have the lock protect the whole H. When you acquire the lock, and you lose the H here. When you acquire the lock, you have this new H. This H is given to you. P points to lock H. And when you release the lock, you're giving up on H. You're just putting it back into lock. I hope that makes sense. So in this example, there was an H that we seen before. And so there was an exercise of maybe, I don't know, should I do it slowly? No, I don't. Okay, so at every step of the way, you have these heap predicates. I mean, I can explain, but maybe that's clear already. I don't know. Maybe I'll come back if I have more time. What is interesting though is that suppose you have this function instead. This function f increments the reference r by 1 inside of a critical section, so that's allowed. And so the function, the main here would be calling this function twice, acquire the lock p, and a set r is equal to 2. So that makes sense. R is equal to 0 at first, and you are calling the function twice. So probably that at the end you have 2. You don't have any funny business of competition in R because you have locks, so it's all fine. You should be able to prove it, but in fact, you cannot with the rules I've presented to you, because the locks protect some resources, and this resource is in fact called an invariant. It doesn't change. When you acquire it, you just get the invariant. And so for this, having an invariant is not enough. The invariant cannot be that R points to 0, because R doesn't stay at 0. It could be R is bigger than 0. That would be indeed preserved by the function f. But then the fact that R is bigger than 0 is not enough to prove that R is equal to 2. So you need something more. So instead of this, so I rewrote the program with just a parallel composition of basically the two functions. So instead of this program, you can annotate it with some auxiliary values. Oh yeah, so the point was you cannot have an invariant here. Yeah, again, that's what I said before. So what you do is you add 2 new references that do basically nothing for your program, because they are just thrown away at the end. However, the first one is passed to the first thread. The second one is passed to the second thread. And so once you have those auxiliary variable, you are able to talk about the contribution of each thread. And so exercise, give a lock invariant that allows to prove this program. So you can, there would be something like this. P protects all of the result, no, in fact, not all of them. So it's a bit of a mouthful. So P protects this invariant. The invariant contains entirely R, and it is necessary because the R is what is used by the 2 threads in writing. they are both writing to R, so we need a full permission on R in the invariant, because it's the only way we can access something on both sides. However, what is useful is to say the invariant contains just enough of R1 to be able to talk about its value. So we have R1 that points with permission 1/2 on N1, and R2 points to N2 with also half of permission, and those two values are related. Those three values are related, saying N is the sum of N1 and N2. So it's a simple example, but if you have a more complicated program, it is generally something like the global state is the combination of the local states of the threads.
Quick question.
Yes.
How are you able to write to R1? How are you able?
How are you able to write to R1 if you only have half a permission?
Yes, that is a good question. I will just.
Okay, thanks.
Okay, so how does this go? We allocate 3 references. We have full permission of all of those. We split those permissions of R1 and R2 into 2 things. We put them in H. When we put them in H, we are losing the information of N1 being 0, N2 being 0, but it's still there outside of the H, outside of the invariant. So we will be able to say things about it. So we create the locks. So what is left after this is just R1, R2, and the information that the lock protects this invariant. We can split the lock into 2 parts because it is duplicable. And then we have to prove the left thread with, of course, the lock invariant, but also the fact that R1 points to 0 with permission 1/2. Same on the right with R2. And so how does this go for one of the threads? So you acquire the lock, so you get back H. Then you split, you know, using the existential rule that for some N, N1, N2, such that N is equal to N1 plus N2, that this holds. So in order to do this right, you have you need just a full permission on R, so that's fine. You can prove that you can go from R points to N to R points to N plus 1. No problem here. However, to do the right on R1, you need to know to have the full permission on R1. So you need to combine this one with this one. Of course, when you combine them, you get the information that N1 is equal to 0. So you have full permission on R1. You increment it. You get R points to 1 with full permission. You split R1 again. So by choosing carefully in a very smart way, N1 is 1 now, and N2 is just the N2 of before. And so we can fold back to the invariant H, and we can finally release the lock P. And so at the end, we have stored basically the contribution of this thread into a variable R1. And so we are able to do, of course, the same for the right thread. And so at the end, we get the information that R1 points to 1, R2 points to 2 with half permission. We acquire the lock, so we have this invariant that comes back. We can combine it back to have the fact that R1 points to R1, R2 to 1, sorry, and R points to N such that N is equal to 1 plus 1. Oh yeah, I forgot to mention. Yeah.
I cannot claim that I followed every single step there, but one thing that I was trying to wrap my head around here is that in some way you need to use the fact that associative addition of plus 1 is commutative in this sense, and I'm struggling to see where you, so basically where you see the other interleaving, where you reason about the other interleaving of this, and have to show that they're equivalent, whereas where's the proof burden of that?
So I think the answer in general is that you have invariants on one side that let you handle the resources, and you have some kind of notion of monoid. That's the most general version, so that you can combine things in maybe a bunch of different orders, but still. Okay, no, maybe the most helpful thing is that the proof burden is to find an invariant and to find this relation between the purely logical state of each of your threads. And so basically this says the current state can be explained by the history of every thread. So you say for every interleaving of your history, you will get something like this. So that's basically the proof burden. So of course, if your contribution are additive, that simplify things, but you can do things that are more complicated. So if you say, if you formalize a queue, you'll have some interleaving, you'll have some weird things going on when it's popping. So yeah, it can be complicated sometimes to even specify what you want.
So is there any guarantee that I can always express this as an invariant in some way? Is there any result of that type?
I'm not sure. I don't know what it would look like, but yeah, that maybe there are some completeness results, but I'm not aware of them. Okay, so this was a bit weird because you had to introduce you have to change your program in order to prove it, so that's not satisfactory. So the standard way is not using those ghost variables, those auxiliary variables, but you use some kind of okay, why is because what if you have an arbitrary number of threads? Would you need to modify your program in an arbitrary number of variables? It would be a bit strange. You need some erasure theorem to talk about the preservation of semantics. And in general, it should not be in the program, but because that's reasoning about the program, not in the program. So the standard way of dealing with this is to use ghost state. Here is how they work in Iris. So you can allocate for at any point in your proof using this very strange implication. This means that this is an implication that you can do at some points, but not at every point of your program. You need to go you need to be able to say basically, I'm about to do some step so that it forbids some circular reasoning. Okay, but basically this is allocating some ghost state stored in this ghost variable gamma. Gamma points to ghost of A. This doesn't say anything about the real memory, but it says something about some ghost memory, the ghost resources basically. And so if you have a resource algebra, you have a bunch of axiom when you define a resource algebra, but the most interesting part is that you can combine two ghosts. So if gamma points to ghost of A dot B for some dot, then you can split it into A and B. And what is important is that when you have when you have the combination on A of B, you know that it implies that this combination is valid in some way. And so you could define, for example, that R points to N1 and R points to N2 are two ghost things. So it's not the same, it's not a heap predicate anymore. It's a weird thing. This would imply, for example, that N1 is equal to N2, sorry. And in fact, heaps in Iris, the heap predicates are just one example of this ghost resource algebra. So it's a composition of the fractional resource algebra and the agreements resource algebra. Okay. I've presented weakest preconditions before, so I'll just skip all of these. PE phi is the same as P implies WPE of phi. I've showed you how Iris works before, so it's just I just skip. And finally, This is not by me. This is with Paolo De Villena and François Poutier. How you do proof about effect handlers? So it's quite verbose, but the important things is here when you want to perform an effect, do V, so op V, I think, in the lecture in Sam's lectures. Then you need some you have this information in your protocol psi. So maybe I should present the value rule first. So the value rule is that when you return a value, it has to satisfy the post condition, and the post condition is phi. It's presented inside the brackets, the curly brackets. And psi is not mentioned for the value because it's not performing an effect, it's just a value. So psi is the protocol for effects. What do you do for effects? When you perform an effect V, then psi must have this information that V is an allowed effect, and psi is a bunch of pre and post condition for every effect, basically. I'll skip. So you have the bind rule. When you have no handler, the bind rule is fine. When n is a evaluation context with no handler, then it's no problem. If you have any evaluation context, then you need to say, so you have the bind rule, but the E inside is forbidden to perform any effect. And so the rule for handlers is the following. So how do we read this? So try of E with HR. This is like handle E with H for handlers, and R is the branch for return value. So we'll read this first. So if you can prove that E has some post condition phi with the protocol psi, then for every value, you know that, so when it returns a value, you'll end up in the branch of R. So you know that R of V should be valid in some post condition phi prime if you give it a value that satisfies the normal post condition of E. And for the handle part, it's a bit harder to read, but basically you are here if basically you could perform some effects inside the protocol psi, then as long as you can prove the continuation holds for the post condition that you have in the for E. So that's your hypothesis. Then you have to prove that H of V, the return value, and K, the continuation, holds with the post condition that you had here. So it looks like almost you jump from places to places by saying you have a post condition where your precondition when you perform an effect. This goes into the precondition of your H and back. H has the burden of saying if I'm calling the continuation, I have to have some precondition there that will become the post condition where I called the effect. I perform the effect. So it's like go-tos. It's not very hard, though. If you have to, this is presented in a way that actually doing proof with it is possible. But then it's a bit hard to present in 5 minutes. Plus, it's not my work. So, and you have the same for deep. So deep can be encoded with shallow with a recursive thing. So this is an encoding, but however, the reasoning rule will be the same as if deep was not an encoding, but just a primitive construction. And so it's the same. However, when you do, you have this extra hypothesis, then that is itself recursive. Yeah, I forgot. Deep handler is in fact this whole thing. See the paper. All right. Then you have a bunch of modalities, but we don't have time. It's actually cheap. The lab rule is good. I'll leave it for now. And thank you. Yes, Sam?
It's impressive how scalable this is, all these things you added to separation logic. It's worked really nicely.
Yeah.
Are all of these features supported by Iris?
Which ones, which features do you
The ones you presented today?
Yeah. Yep, I think so. I don't think, I cannot think of any that is not, which, I mean, yes, so the entailment is not in Aris. It's just entailment like a V dash. And it means a slightly different thing, a way more complicated thing, because it's talking about a whole different notion of iprop, which has very recursive, very, I mean, the semantic model is much more complicated than what I have here. So there are things that are, I mean, there are things that are different, but it's basically, yes, available. And so, this was in Iris. We're also working on this for Camel, and it's inside Iris as well. I should also say that because it's in Camel, there is a bunch of things that you can do for pure programs. And for pure programs, we actually do not want that much Iris because we don't need it. So we have a smaller mode that is just pure.